Hi there, this is Jacob Nash, and in this video we'll be looking at trig substitution. So, camera on, yeah, sorry about that. Um, Trig substitution, not the same thing as trig integrals that we did in the last video, because if you recall, I already mentioned that in the last video that those begin with trig identities to start, but these will not have trig identities at the beginning. You'll plug it in, you'll plug in a trig function later on. And obviously you'll understand that later on. But the thing that I need to say in this video to begin is that I will show a few examples, but what you really need to do is as many practice problems as you can. As annoying as it may seem, it will actually get way quicker after you just do a few. Because then you'll start to be like, oh, I get the process. So what I say in this video, this is a very extremely difficult concept to explain, mostly just because there are lots of possibilities, but I try to lay out the general process that we do. So I already pretty much talked about this. So let's go ahead and look at an example of what this will be like. So with these, here's how it's always going to look. It's always going to be a square root of two things added or subtracted. Three possibilities: a number minus x, x minus a number, or they're both added. Here's what you do in all three of those situations. All right, let's see how this is. We have a number minus x, so we just say x equals the number, and you might say, hey, why isn't it 4? Careful, a squared is right here. This is just a, so it's got to be 2. So it's always got to be square root of what number you see. Then, what about that? Sine. Okay. Now you might be thinking, what the heck's the point in this? Why are we uh you know saying x equals that? Well, why is it's because we can't do this integral, right? That you might think, okay, I can just make that to the half power and do reverse chain rule. No, that's terrible. Can't do that. This is what you have to do. And the point of this is that we're going to replace x with this later on. What's the deal though? This dx can't have that. Got to replace that with something because you can't have two different variables. And you might say, why is it theta? I know we usually use u, but this time we're doing theta because these problems are so complex and can take so long, you might have to do u sub later on. So it's better to just use theta because that's usually associated with trig. So you gotta forget about that. We'll talk about that later. You gotta find dx. Um, and what's the derivative of 2 sine theta? Oh, pretty easy. Just 2 cosine theta, d theta. Don't forget about that right there. Then you just plug it in. So this x squared, we replace it with this. Hey, why is there a 4 instead of a 2? Ooh, squared. So the squared doesn't only apply to the sine, it also applies to this. So we get 4 sine squared theta. Don't get mixed up by don't say sine theta squared. Sine squared theta. That's the way that we do it for that. Now, also another mistake you might make is instead of you might do only d theta, but don't forget about this. That's the whole reason why we did this. You have to replace dx with this whole thing. Another thing, probably the third thing that you might be thinking, hey, why isn't it divided by 2 cosine theta? Isn't that what we usually do? Well, don't overthink it. That's because typically when we're finding dx, that's when we're doing the u substitution, we're actually doing u du. So this is kind of reverse, but you don't overthink it. What you see is what dx equals, so no, you don't have to divide. It's just multiplied this time. Because we're replacing dx, we're not replacing d theta. Now, what do we do here? Why do we factor out that 4? Because the next step is always to replace with a trig identity. I see sine, I see cosine. I know for a fact that the trig identity that I'll use is sine squared plus cosine squared equals 1. So I need to make it possible to even use that identity. That 4 is stupid. I hate it. So I'll factor that out. Now, hey, there we go. I see something that looks like the trig identity I know. Bingo. Plug that thing in. Cosine squared theta. And don't forget, this carries on down here. Now what? What the heck? Now what do we do? Well, luckily, the square root, we can say goodbye to it because it's stupid. You can take the square root of 4, it's 2. You can take the square root of cosine squared theta, cosine. Well, what about now? You might think, do I have to do integration by parts? No, careful. Never do integration by parts unless you have to. And by the way, you can do something and then go back. You can always, you have an eraser on that back of your pencil, right? Erase. You realize that you did something that was stupid. If it ever gets more complex, that means that you know that you did something wrong. But what you need to do is actually multiply these together. Oh, that's not so bad, right? There you go. Well, now what? Can I do the integral of this now? No, we don't know what that is. But luckily, anytime I see a cosine squared, well, first of all, you wouldn't go back to that. That would be useless because we also can't do the integral of that. That would be pointless. So another thing that I can do is use the double angle identity because I can take the integral of cosine to the 1 or like, so that's the reason why we would do that. You have to memorize these. So now we plug that in. Now I know you might think this doesn't look the same. Well, see, it's 1 plus cosine 2x. It's just switched around and it's also a different variable. Now, why is it 2 instead of 4? Because of this divided by 2. So 4 divided by 2, 2. Now what? I can take the integral of that now. Yay. But there's actually a mini u substitution going on right here. So first of all, this is really, I apologize. It's whoever wrote this skipped the step. And I've said this before. The reason why I'm not writing this all out myself is that adds a lot of time to the video. So that's why. So we can take out that 2. So we can do this. It's going to be a little bit messy handwriting because it's hard to write with a mouse. Okay. And pretend like there's a d theta there. Not writing that right now. So u equals, if you can do this in your head and you get this, skip the video like 30 seconds. But I'm doing this for those that might still not see what it is. What is the derivative of 2 theta? Just 2. D theta. So that means that d theta equals du divided by 2. So hard to write on this. Du divided by 2. So now we have cosine of u plus 1. And hey, replace the d theta that's right here with du divided by 2. So du divided by 2, all this divided by 2. Now, what is the integral of that? It's sine of u. These 2's cancel out. And then you replace the u with 2 theta. And this ends up 2 theta right here just because the derivative, sorry, the integral of 1 is theta, and then this 2 multiplies to it. So that's how we got that. Let me delete that now. Okay. So now you might think that's done. Unfortunately not, because we can't have thetas. We have to switch back to x's, which will bring in this triangle. So the thing is how can we switch back to x? What do I see here? I see 2 theta. I see 2 theta. Here is a rule. Anytime you see sine of 2 theta or anything like that, where in the parentheses, it's not just a variable, use this identity right here. It's going to equal 2 sine theta cosine theta. So now this is equivalent, right? And the plus c wasn't right there, but it should have been. So there you go. Now we have this. And like I said, we have to switch back to x's. So we have to figure out what is sine theta equal to, what is cosine theta equal to, and what is theta equal to. Now, here's something that you might be thinking. Why can't I just only figure out what theta is and plug it in there, there, and there? Because theta is always going to be something that's like arc something, and you never want to do sine of arc something. Like that's not really good to do usually. Most professors or teachers might be like points off for that. So you're gonna have to find out what sine theta equals, cosine theta equals, and theta. Now, here's where we get to this triangle over here. Now, how the heck did I come up with this triangle? Well, doesn't this thing right here kind of look like if I'm doing the Pythagorean theorem and I'm solving for something? That's how it usually looks, right? So that's how. So this 2 right here comes from here because this is really 2 squared minus x squared. Now, how did I know this was the hypotenuse? Well, anytime you're using the Pythagorean theorem and you're solving for something, C is always going to be the first thing, right? Because let's say I was solving for A. It would equal C squared divided by B squared, and then the square root of that, right? So the first thing is always going to be C. If there's a minus, only if there's a minus. If it's plus, if they're both added, that must mean it's A squared plus B squared, right? That's probably obvious. So this is definitely going to be C. This is going to be either A or B. It doesn't matter. That doesn't matter. For the legs of a triangle, it can change. You can do whichever you feel like. So let's just say it's A. Doesn't even matter. So we put that X right here. Hey, how did I get that for B? Well, like I said, this kind of looks like if you were solving for something. So this must be if we were solving for B, that would be equivalent. And you can test it out if you don't believe me. If you do this squared plus this squared, it will equal 4 or 2 squared. That's what would happen. So that's how we made this triangle. Now, how does this help us find what sine theta, cosine theta, and theta equal? Well, first of all, going back to this table, sine is what we used, right? And we have, if we were solving for sine theta, it equals x over 2. So that's how we find out what sine is, right? Sine theta is just going to be x over 2 just using this equation right here. Um, so there you go. Now, how do we find cosine or uh, just the angle? Well, if we put the angle here, that makes this true, right? If the angle's right here, this is the opposite. This is the hypotenuse. SOHCAHTOA, you got to remember that. This is opposite. This is hypotenuse. So if we put the angle, this is why the angle is here. If we put it here or here, obviously not here because that's supposed to be a right angle. That would not be true. So we can use this angle to find what cosine is. So adjacent over hypotenuse. So that's what cosine. And how do we find what the angle is itself? Well, if sine squared equals x over 2 to get the theta by itself, we do the reverse sine, sine to the -1, arc sine, same thing, and arc sine of x over 2. So these three things, plug that, plug that in. See that blue? It's right here. It's from up here, this purple, this red. You can see where I got that from. And that's your answer. So that's why these are like so annoying problems because that's actually kind of sometimes they might be even longer than this because sometimes you have to do an integration by parts or U sub. Never do an integration by parts unless you have to. Always try to multiply things together if you can. I could right here. So basically, to sum it up, the steps are use this table, which you'll have to memorize, to um, figure out what x is, and then figure out what dx is, plug them in, do trig identities galore until you can take the integral or integration by parts. Do whatever you need to do to where you can take the integral. Once you take the integral, switch back to x using this triangle. Ooh. Now, I'm going to show you two other examples. I'm not going to work them out because that would take a long time. And it's really a review of last video. The only new things is just setting up the problem, but this is the same thing as last time, trig identities, um, trig integrals. So these are just showing you how that there can be other possibilities. So see this one, how is it different than this? This is a number minus x. This is a x minus a number. This time we would use secant for that problem. That's the only difference. And that means that the trig identity I would use instead would probably be the one that has secant and tangent in it. What about this one? This time they're added together, so that means we'd use tangent. Wow, that's really the only difference. I it can have a fraction, it can have an x, can that doesn't change anything. It really doesn't. It just means you'll plug in for x one extra time. But don't get thrown off if you see a fraction or that. You always know you'll use trig substitution just by the fact that I see square root of two things added or subtracted. What if it's a definite integral? Well, the only difference is that you don't have to switch back to x, and then you have to plug in a number. Your answer will be a number, and it won't be something plus c. That's the only difference. How do I know it's a definite integral? Hopefully you know that by now, but it's just because there are numbers right here. So here's the problem. It's also written right here. The first thing I do is I see, hey, what the heck to the power of 3/2? Ooh, don't get thrown off right there. Switch that around to 3. Hopefully you know that means it's actually the square root of something cubed. That means the same thing. I see something minus a number, or sorry, a number minus x. A number minus x means we'll use sine. It happens to be the same thing again. X equals sine theta. Dx equals cosine theta d theta. Plug that in. As you can see, we plugged it in. Now we can simplify. So this right here, we can use a trig identity. Since I see sine and cosine, I know I'll probably have to use the one that has both of those in it. And this is equivalent to cosine squared theta. It would be the square root of cosine squared theta, which means it's really just cosine theta. And there's this cubed here, so that's how we got to down here. Cosine cubed theta is now the denominator. Now what do we do? Well, this cosine theta here and this cosine cubed theta would end up making there be a cosine squared theta on the denominator. So then we would get, sorry that there are some skipped steps. 4 sine squared theta divided by cosine squared theta. Tisk, remember my saying? T equals S divided by C. Tisk, I hate trigonometry. So S divided by C, sine squared divided by cosine squared theta is just going to equal 4 tangent squared theta. Ooh, now I can use a different trig identity right here. First of all, why even would we want to? Because you can't take the integral of this. So you obviously have to do something. That's the only thing you can do. So replace it with this. Now, what happens? We have 4 secant squared theta minus 4. Actually, another really good reason why you would want to replace with this is that we do know the integral of secant squared theta. It's tangent. 4 tangent theta minus 4 theta would be what we get. Bingo. Hey, now um we were able to take the integral. But there's something I forgot to say. I sorry that I did. But why did we switch to 0 and pi over 6? Hey, even though you don't have to switch back to x, since you don't, you have to change your bounds. Pretend like it's a language that you're translating to. If we're translating the thetas, these things also have to be in the Thetonian language, if you want to say. Um, so 0 and pi over 6. Well, how the heck did we get that? You use this equation to figure it out. So um, basically, what you do is you plug in what is sine of 0? Sine of 0 is 0. This table right here, gotta memorize that. Sine of 0 is 0. Hopefully you know that. The blue ones are and it's kind of cut off, sorry. The blue ones are what you might not remember from your unit circle, but memorize that table. So that's how we got 0. What is sine of 1/2? Oh, sorry, that's not how it would be, actually. Never mind. So sorry about that. The thing is you do not actually plug in for theta, you plug in for x because these are your x values. So it would be 0. The correct thing is 0 equals sine theta, and then you would do arc sine of 0 equals 0. And then plug in 1/2 here, arc sine of 1/2 equals pi over 6. Now, how did I get that? Well, that's because um, if you do sine of pi over 6, you get 1/2, so the reverse would get you pi over 6. Sorry about that, got a little bit mixed up there. So memorize this table, that will really, really help. And I moved it up a little bit so you can see the part that was previously cut off. So now revert back to here. So we took the integral, this is what we got. These are the bounds that we plug in. Once again, a good reason why to know the table. You got to know the table. 4 tangent of pi over 6. Tangent of pi over 6 is 1 divided by square root of 3. And so that's what it's going to be. 4, 3 root 3. Root 3 threes. Sorry. Root 3 divided by 3. And then 4 times pi over 6 can simplify to 2/3 pi. So once again, you don't have to switch back to theta, or you don't have to switch back to x, but since you don't, you have to change your bounds. Last thing for this video, what if you have something like this? Still, trig substitution is the answer. But sorry, sometimes it's hard to get the laser turning on. But this doesn't look the same, right? It doesn't follow one of these 3. Well, is there any way that we can make this look like one of these? Yes, and it's by something fabulous that you might not remember called completing the square. Hey, if you don't like that, another thing you can do is find the derivative, or use the derivative to find the maximum, min or max. And if you do that, then that will also give you what this ends up being equivalent to this. So you can do that as well if that's more fresh on your mind, but it's actually not hard. I have it written right here. Plus, I have a video that I made kind of a long time ago in 2021 in the description for a 4-minute video about how to do this, but I'll have it quick here. So what you do to complete the square, I have this right here. I put it right here. I set it equal to 0. I subtract the constant on the other side. Then I add b divided by 2 squared to both sides. B is 2. 2 divided by 2, 1. 1 squared, 1. So I add 1 to both sides. And then that gets you in -4 on the other side. You add it to the other side to make it 0 again over here. 4. And then you basically it's a little bit hard to verbally explain, but the colors hopefully show you what you do. Forget about that 2x now, and you just do this, and the squared's now here. So x plus 1 squared plus 4 equals 0 is the correct complete the square. This method always works. Longer video if you need. And also, like I said, you can also take the derivative of this and set it equal to 0. If you did that, you would get basically this same thing eventually. So whichever you prefer. So that's the only thing different this time. And I'm not even going to really go, since this video has already been long and hopefully you already see, I'm not going to explain how this problem works, but that's only to show you that that's how you would get to this, which now would be one that would fall into this category since they're added. And then same process would exist. You do, no, actually there is one thing that's a little bit different for this. So this time it's not going to just be x, it's going to be x plus 1 since there's that. So x plus 1 equals 2 tangent theta, because we want to replace x plus 1, not just x. So that's the only difference for these types of problems. But it's the same thing, and since it's indefinite, you would want to switch back to x at the end, as is done in this problem, and use a triangle to do that. So that's the end of this video. This is definitely one of the harder calculus concepts, but as I mentioned at the beginning of the video, um, practicing is the best way to get through this. Do as many as you can, and then it will be way easier. So good luck with that, and then see you on the next video.